Hello, and welcome to the Scientific Odyssey. The Scientific Odyssey is a mini-part journey into the history and philosophy of science. My name is Chad Davies, and I'm the writer, host, and producer of the podcast, where we consider the ideas, processes, and results of over 2,500 years of scientific inquiry and discovery. Episode 4.1, Thoughts on Rosetta. This is something I'm going to do from time to time. Every once in a while, something happens in the world of science that just needs a little bit of commentary, something I think that's important enough or interesting enough or just amazing enough that I'm going to release sort of live-time comments into the feed. As such, this is not one of my typical scripted episodes where I've sort of worked out everything I've thought about and kind of planned how the flow of the episode's going to go. I've got some thoughts about what I want to say and what I think is important, but this is going to be something a little rougher, something more spontaneous, I think I would say. So if you've been watching the news today, you've probably seen the information coming out from the European Space Agency. The Rosetta mission over the last couple of weeks has been in orbit. It's in orbit around a comet that I'm not even going to try to pronounce the name of, but it's P67 is what it's getting called. The Rosetta mission, the orbiter, has been in orbit for probably close to 2 weeks. And today it released its lander, and the lander descended down to the surface of the comet and did something just really amazing. And that is, for the first time in human history, we had a lander soft land on a comet and start taking data. And that's kind of what I'd like to talk about in this supplemental episode. I'd like to just say a few words about that. A metaphor that I use in this podcast that I really like is this idea of an Odyssey, that sense of getting on board a ship and going someplace, somewhere that you've not been before, seeing horizons you've never seen, sights that you couldn't have imagined. And I can't think of a better metaphor for this particular discussion. What an Odyssey the Rosetta team has been on, the European Space Agency's team that has sort of guided this mission from its inception until today's just really amazing work, and the work I'm sure that's going to come from this mission going forward. A mission that I think is going to last quite a bit of time, and it's going to provide us an amazing amount of data. And so I kind of would like to, if I could, just start at the beginning and talk a little bit about what goes into an Odyssey of this kind. You know, somewhere this idea, somebody had to have this idea. They thought to think that somewhere along the line, hey, what if we could go to a comet? What if we could send one of these robotic space probes to a comet and not only go to the comet and take a look at it, but then to do the really audacious, amazing thing of what if we could land one of these landers on a comet. And the thing that's interesting about this is none of these ideas all by itself is new. You know, back in 1986, several nations sent various probes to Halley's Comet. And, they flew through its tail, as the coma and the tail of the comet. They imaged the comet with the technology that was available to them at the time. And then, of course, we've had all kinds of landers land on both the moon and on Mars. But this is just something a little different. Sometime, maybe 20, 25 years ago, somebody had to have that idea of, let's go to this comet, or just some comet, and let's land a lander on the comet. What a great idea. And then all the planning had to start. The engineering and the how do we build this probe, this thing that's going to go out to the comet, and how do we build the lander? And what kinds of instruments, scientific data taking instruments, do we want to put on both of those platforms? And what, if we're going to do that, what are we going to need? What are our power requirements going to be? And what types of instruments are we going to include? And maybe do we include this one, but because we don't have enough space, that means we got to take this other one out. And a team had to come together and to plan this mission. And they had to plan things like, what would the trajectory of the voyage be? And it turns out the Rosetta mission, launched about 10 years ago from the Earth. It makes several passes through the inner solar system to get that trajectory just right. Because what they've got to do is they've got to fly this thing. And when I say fly, it's not fly like you think of on Earth, where you're going to, have something that has control surfaces and it's going to be moving through air. And so the air is going to exert forces on the control surfaces that will allow you to steer the craft. Rather, this is something where they've got to use carefully timed thrusts or bursts of air. But more than that, what they have to do is they have to use gravity. They have to be able to sort of understand the laws of nature well enough that they can say, okay, we're going to use the various effects of the planets in the inner solar system, Earth and Mars, to guide our trajectory, to steer our craft out so that the craft is going to catch up with this comet. And the comet's moving at about 54,000 kilometers an hour through space. And, they have to maneuver this thing first with gravity, and then as they get a little closer, they have to use these maneuvering rockets to get the probe in so that it's able to go into orbit around this comet, which is a really difficult thing to do. And so, in order to do all that planning, then they've got to actually construct the orbiter and construct the lander, and the amount of engineering that goes into that, and all of the sort of what's the technology and how much power do we have to generate from solar panels, which is what this craft uses both on the orbiter and in the lander, and how do we build that so that it can survive not just the launch, which the launch is an extraordinarily violent thing for something with delicate electronics. The launch, it shakes and it rattles and it vibrates, and there's all of this going on, and you've got to sort of protect the craft and build the craft more strongly enough that it's able to survive that. But then, the craft spends 10 years in space, and the lander is inside of the craft, and the craft sort of stays awake and communicates back, but the lander doesn't. I was talking with one of my classes today, and I think the best analogy might be, it had been in somebody in, say, 1995, had gone to a Best Buy or, whatever it was back then, a Circuit City, and had bought a laptop. And they charged the battery of the laptop up, and they made sure the laptop was in great shape. Or maybe they built their own laptop. Maybe that's a better analogy, but it's in great shape. And then they put it in a drawer for 15 years. And maybe, they pull it out of the drawer every once in a while to check it until about 10 years before they want to use it. And then they put it in a drawer, or better yet, they put it in their deep freeze. And it stays there for 10 long years. Well, that's what this lander does. It sits in the orbiter. It sits in the Rosetta spacecraft. And other than some nominal checks just to make sure it's okay, it doesn't do anything. And then 10 years after launch, when the orbiter's in place, when it's done a number of maneuvers to get it into an orbit around the comet that's only 10 miles above the surface, it releases this lander. And, I can't imagine being on the science team. These guys who have men and women both, who have spent years of their lives and countless hours of their careers in part dedicated to this mission, who have worked on the science instruments and the apparatus to make sure that they're just what they need. They've put them on this thing, and then, the day that they're going to turn on the whole thing, the day they're going to turn that lander on and check it out, and just waiting to see if it works. So I didn't see if the laptop turns on. And when they open the lid, that, the startup screen happens, And that happened. That's what's really amazing, if you can imagine that. 10 years after you put the laptop in the deep freeze, you open the lid, and lo and behold, you get that startup chime. Well, then, of course, what they do is they have to go through a bunch of self-tests, and they have to get the orbiter in just the right place. And the thing that makes this just really amazing, of course, is, it's not just that the comet's moving at 54,000 kilometers an hour. It's that the comet's tumbling. And so, you've got to find a spot on the comet that is pretty free of debris, because when you drop this lander down, it can't land on a boulder, or it can't land in some hole or something, because then it'll tip over and it won't work. And then, you let the lander go, and about, 7 hours is what it takes. Because when they release the lander, and it's moving at about 2 miles an hour relative to the surface of the comet. 1 meter per second if we use metric units. And this lander slowly descends down to the comet over the next 7 hours from that original height of about 6 miles or 10 kilometers. And all the way down, it's sort of, you're taking data and you're checking out, and you're hoping to get telemetry. But then the thing has to land. And the thing that's just so amazing about this, the thing that just blows my mind, is it all worked. A couple of weeks ago, we've got a couple of examples of just how hard it is to do spaceflight. We had two missions, both by private companies, that failed. Unfortunately, the Spaceship Two mission by, I guess, Virgin Galactic, cost one of the pilots their lives. I mean, it's going to space is hard, and it's dangerous, and it can be deadly, as we well know. And yet, here are these guys. They took this huge risk. 10 years, millions, maybe billions of dollars invested in the spacecraft, and the lander's only a small part of the mission. But it's symbolic of just the kind of, sometimes the big risks and the big efforts and the big chances scientists will take to discover something so really cool. So I spent all day today, and I got caught up in this. It was one of those things where, starting this morning, I got to school and just started following this as the lander slowly descended down towards the planet. And the last 2 hours of the descent happened during one of the physics classes I teach. And it's an introductory physics class, and it turns out that on this day, today, because of the way I structure my class, is actually when we talked about projectile motion. And the thing that was so amazing about this is we're watching the press conference, and we're viewing what's going on in the control room there with the mission scientists and the project managers and the mission engineers. Is my students are in here, and they're using a video capture software package, and they're looking at the motion of a ball that's been fired from a projectile launcher as it travels through space, and they're doing an analysis of that motion. And the thing that just struck me is, 500 years ago, give or take, Galileo Galilei did experiments on the motion of objects. And he didn't have projectile launchers and video capture software and all of the really wonderful educational tools I've got in my classroom, which makes his work even more amazing. But it's the same spirit of discovery. It's the same journey. And he set us out on that journey 500 years ago. And that journey, step by step, starting with Galileo through Descartes, huge figure in understanding how this work happened with Isaac Newton, who figured out the laws of motion and discovered gravity in our first way of describing it, And everything from those guys through guys like, Maclaurin and Hamilton using Gauss, the electronics and the some of the telecommunications software but hardware through Maxwell's equations and Maxwell's work in electricity and magnetism, all of this stuff up to the invention of transistors based on quantum mechanics in the labs there at Bell Labs, up until the present, is this incredible, amazing, long scientific and technological journey. And then there we were in my class, and it was just, I don't know, it's such a hard feeling to describe what it was like to realize that my students were there at the first step as we were watching, in a sense, this momentary and just momentary end point on that journey. And it was a wonderful moment of transposition, of seeing these two endpoints in the same room at the same time. Really made me just sort of appreciate what it is that science gives us, what it is that science brings to us. And it was really, really neat in the classroom because as we had this going, a lot of times when I'm giving labs, my students are like, oh my gosh, it's another science lab. Gee, how boring is that? And for them to be able to see that what they were doing, that however far away it might be, was on the same journey, and you could see some energy and excitement in their eyes. And it was one of those days where it was just kind of like, as they started to discover things, they realized that they were on that journey, that same Odyssey that began 500 years ago with Galileo, and then in this day culminated, though didn't finish by any stretch, in the landing of something about the size of a washing machine on the Comet. And the thing is it's, sometimes it sounds like, oh, well, is there any drama in this? Can you imagine? I mean, we got to watch the mission scientists, sit there and they're waiting for the data to come back from the lander. And the problem with this is the comet's so far away that it takes time for the electromagnetic radio signals that the lander broadcasts to the orbiter and then the orbiter broadcasts to Earth. It takes a little over 26 minutes for that, almost a half an hour for that to get to the Earth. So, it's one of those things where there was a point there where you realize the lander might be on the surface, but we're waiting for the data. And you could see the tension in these scientists' bodies, these engineers, these project managers. You could just see the tension in their faces and in their bodies as they realized that in this moment, all of that risk and all of that planning, this was going to be the moment that determined it. And of course, as we know now, the landing was successful, though not without its issues. And the jubilation and the joy and the excitement of discovery on their faces and in their body, it was so amazing and so gratifying. It was one of those things where in watching that and in seeing that, you see just how wonderful science as a method and a methodology really can be. As we were watching the feed, and as my students were working, I'd circulate around the room and make sure that they were making progress on the work they were supposed to be getting done. And more than one time I had students who would stop me and they would ask, so why is it that we're doing this? Why are we spending money to go to this Comet? Why do we want to know? And it was just one of those great things. And I hope, in me sort of bringing that up, if you've listened to the podcast here for a while, you have that answer. It's because we want to understand. We want to understand the relationships that govern the universe. The specific science objectives is to figure out what's the composition of this comet, to understand what its structure is. Over a longer period of time, the hope is that we'll be able to sort of closely observe the process that as the comet gets closer to the sun, how it outgasses and how that changes the comet and those sorts of things, and be able to observe that over time. And it's really a wonderful thing because the hope here is, of course, what we would like to do is comets are thought to be unmodified leftovers from the early formation of the solar system. And so the idea is if we try to look at stuff here on Earth or, on Mars, the problem is those worlds, because of their formation scenarios in accumulating material and that heating up the worlds and that heat melting the stuff and causing it to differentiate, to separate into lighter and heavier stuff where the heavier stuff sinks, that we no longer have a good sense by looking at the Earth or Mars or the Moon what the early solar system, the very, very early solar system might have been like before the formation of larger worlds. Whereas with comets, that material never went through that differentiation process. So the hope is we'll get a better sense of the building blocks, the small pieces that originally began to make up the solar system as it started forming, And so, there were really good science goals, and there are really good science goals with this mission. But the thing that's just, I think even more than that, if you'd ask the scientist, to dig deep down below, okay, what are your specific scientific and, objectives, blah, 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 for the mission? I think any scientist would say, well, we want to understand. We want to know. We want to have the knowledge of how this is put together. And I don't know that anybody in humankind is going to benefit from that. But who knows? Maybe one day, the data gathered by this Rosetta mission, will allow us to go to comets and mine them for water, or mine them for materials or minerals for a growing society that maybe expands beyond the Earth, expands out and takes those first steps out off of, as Carl Sagan so prosaically puts it, off the shores of our cosmic ocean, to where human beings begin to venture out off of the Earth, the only home we've really known, and into something much greater and much deeper. And it's just, again, as I thought about it all day long, I just thought about how audacious the mission was. How audacious that maybe 20 years ago, I don't know, that a small group of scientists with the European Space Agency said, hey, what if we do this? What would it take? And then for governments and for people and for individual scientists to believe enough in that idea to commit their time and their energy and their resources, both material and intellectual, into that endeavor. And what a wonderful thing that is. And so, I think it behooves us for a minute as we, consider this first day of the lander's mission, though not the first day of the orbiter's mission, the first day of the lander's mission, the great success. But also there's some challenges with this. One of the things that happened is this lander descends down towards this comet. The problem is, since the comet's so small, it's only about, I don't know, what is it, 3 miles across, something like that. It's about 5 kilometers. What they, the problem is it's so small and there's so little mass in this thing that it doesn't generate much gravity. So, they say that the weight of this probe, which would probably be, it's probably about the size, like I say, of a washing machine. So maybe it's somewhere between 30 and 50 kilograms. Okay. Well, that's about 100 pounds on the Earth, maybe, 150 pounds of weight here on the Earth. Well, what they say is that because the force of gravity generated by this comet is so low, that on the comet, this 110 pound, what we'd say is probably, closer to maybe 300, 400, 500 Newton weighted object on the Earth, the force of gravity is so small that it has only 2/5 of the weight of a single penny on the Earth. The force on this thing, if we put it in metric units, is about 0.01 newtons. It's tiny. And so the question is how do you get this thing when it hits the surface, when it lands, no matter how slowly? And, they designed it so that when it landed, the landing gear absorbed most of that energy. But how do you get it that when it does that, not to bounce back off? How do you get it to stay in place? Well, they had some really ingenious ideas. They thought, okay, what we're going to do is we're going to fire some harpoons. We're going to use some kind of explosive charge, fire harpoons into the surface of this thing, use the harpoons to kind of pull the lander onto the surface, and then use some sort of ice auger things in some parts of the lander to sort of attach it to the surface so the thing doesn't float off. Well, of course, space is hard. And space travel is hard. And so what happens when you do space travel is not everything always works the way you think. So what they think now is that the harpoons might not have fired. And so this thing came down and it hit and it bounced and it rotated a little bit and then landed a second time. So the big joke at the European Space Agency is not only have they landed on a comet once, they've landed on the comet twice. But the challenge that faces the engineering teams now, and it's not like they can go out there and just say, okay, well, I think we'll fix this thing up. But the challenge now is, how do we get this thing to stay on the surface of this comet? So far, the lander seems to be sitting there pretty well. And the really cool thing, and this is the part that just blows my mind, is what they've managed to do is they've managed to take samples, and I'm not sure if the samples were taken on the way down during the descent, that they had some instrument that was able to sort of get dust and gas samples on the way down, or if they've actually taken a surface sample off the surface just yet. And the press releases from ESA haven't really said at this point. But what they've managed to do is feed those into a common instrument used by chemists called a mass spectrometer. And again, and we've mentioned this before, if you've watched your standard crime procedural, forensic science shows, they talk about doing things with a mass spectrometer all the time. And so they've managed to feed samples into a mass spec and transmit that data back to the Earth. And I guess the thing that just is amazing to me is that means as a species, we human beings are doing chemistry on a comet. And that just is audacious. That is so amazing. That is so phenomenal that we are able to do that as a species. And I guess as I would wrap up, one of the things I might say is, as a species, we do some pretty dumb things sometimes. And, there's a lot that you can look at through history that says, boy, I don't know. But this is one of those things that's it raises our species to its highest level, where we do and we risk and we gain so much out of our brilliance and our creativity and our willingness to share resources and energy and intellectual ferment and ideas. So if you haven't had a chance to go out and take a look at some of the data and the information that's coming out, some of the pictures, it's amazing. The lander shot back or sent back the first images from the surface of a comet. Think about that for a minute. We have images from the surface of a comet. It's pretty amazing, and I hope you'll go out and take a look at them. So I hope this hasn't been too bad. I hope I haven't rambled too much. I appreciate everyone who listens to the podcast, and we'll be back on Sunday, I think, with a regular episode. But until then, full sails on your journey.